Hello, everyone. Welcome to this new technical webinar of the LoRa Alliance about augmenting LoRaWAN devices with the Internet Protocol. Today, we are going to explain how the LoRa Alliance has contributed to make a release of an official technical specification to support this adaptation layer for IPv6 over LoRaWAN. My name is Rémi Demerlet. I work at Semtech as Marketing Director, and I chair the IPv6 Task Force of the LoRa Alliance. For instruction about how to use this console, you can here read different instructions. You can find the webcast slides in the console. And at the end of the session, there will be a session for question and answers. You could use the box to send your questions, and we will tackle those questions at the end. Let's take a look to the LPWAN market. We know it's a growing market because of demand of customers in many verticals. We have observed a great, of course, inspiration from the internet application, customers using legacy system on internet, requiring adoption of internet protocols. For all LPWAN technologies, this is a common challenge to support internet protocol because LPWAN are by default in constrained situation, limited bandwidth, limited airtime, etc. In the LPWAN market, the LoRaWAN technology takes the lion's share of revenues. It's keep growing year over years. All IoT devices, they use always a sensor sending data to a platform. But by default, as said, it's not internet-based. And that's a challenge when for developers, they must integrate the extracted data from IoT sensor into existing customer system based on internet. For that reason, the LoRa Alliance has announced last May 17 the official release of technical specification. This adaptation layer allows to overcome the problem of non-interoperability of devices between LPWAN and reduce the challenge of developers to integrate data into existing systems. We will give examples of application for this adaptation layer. I would like to welcome our speakers for this panel, namely Dominique Bartel from Orange, Hussein Al-Hassan from Aclio, and Professor Laurent Toutain from IMT Atlantic. In the agenda of the webinar, we will start first to explain the challenges, why Internet Protocol for constrained IoT. We will have then more explanation on the long history of Internet protocols through the Internet Engineering Task Force, and all, I will say, the development of header compression techniques to improve the efficiency of LPWAN networks. One of the great examples of this is the SCHC technology, where we will have illustration and demo by Aclio. The essence of the technical webinar is to explain why and how you can apply SCHC to LoRaWAN. And there will be an illustration with use case of DLMS, etc., and other applications that can benefit of this adaptation layer. Now, without any further delay, I will invite Dominique to continue with the first part.
Thank you, Rémi, for the introduction. So why is it that we're talking about internet protocols here at the LoRa Alliance? Well, Much like the LoRa Alliance has federated an ecosystem around low-power IoT devices and long-range low-power networks, Internet protocols have long federated a large variety of networks, namely computer networks in the 80s and 90s, then to encompass telecommunication networks in the years 2000, including the wireless version of telecommunication networks, cellular networks, and even more recently, media broadcast networks, voice over IP, TV over IP, for example. So how do Internet protocols support this variety of services? Well, mostly through a very simple networking layer, the IP layer, and an upper stack of various protocols that have the nice properties needed by the various applications. And you probably have heard of HTTP and TCP, for example. You probably use them daily as you browse the web or run web services. And IP also harmonizes the various underlying link layers, either Ethernet, Wi-Fi, cellular, so that you don't have to think about what kind of transmission technology you're using as you browse the web, for example. And this variety of protocols are developed at the Internet Engineering Technical Forum, the IETF, which is involved in developing standards for things such as security, operations, routing, etc. And so, of course, the IETF has been aware of IoT for a long time and has been involved in the IoT for over 15 years now. One example being the development of the CoAP application protocol, which is similar to HTTP, but for the IoT. Another example being an adaptation layer for the IEEE 802.15.4 radio transmission that's used for smart home or smart industry, for example. However, some low-power wide area networks are still non-IP capable today. And the reasons that are being mentioned for that are that IP is maybe too chatty, has too much dialogue going on back and forth, or too heavy, too large headers, too many bytes to be sent, to be compatible with the LP1 constraints, typically payload size, data rate, energy expenditure, for example. If we look at those arguments, well, not all Internet protocols are chatty. For example, CoAP was designed very specifically to be very quiet if needed, and UDP obviously is not chatty. If we look at the second aspect, being too heavy, it's actually true that if you want to send a few bytes of sensory data with regular IP protocols, you'll probably send that data within a CoAP message, and then the CoAP message will be transported into a UDP datagram, and the UDP datagram will be sent within an IP packet. And all of that is going to be inserted as a payload into your link layer protocol, for example, LoRaWAN. And CoAP UDP IPv6 typically will add 50 to 80 bytes to your payload, to your data, which maybe was only a few bytes. So that could seem like a very huge overhead. And actually, people often say, well, IP, UDP, all these Internet protocols provide many features that we don't need. And so if we don't need those features, we shouldn't be using all these fields in all these headers and sending all those bytes for nothing. And that's absolutely true. We agree with that statement. We argue that if we don't use those features, then all these fields, all these bytes will probably carry well-known values or constant values that are easy enough not to send using some techniques that we're going to show you in this webinar. And by doing that, we are able to efficiently support IP protocols, and thereby the LoRa Alliance can extend its business to the many IP-based applications and services that are out there ready to grasp. And the Alliance can also make use of the resources that are scaled to the internet protocols that know how to develop applications using the well-known REST APIs, for example, and also use security protocols and security models that are well-known, well-proven, well-scrutinized. It also reduces the need for protocol translation gateways, which are often difficult to design and maintain. With this, I'm handing it over to Laurent for a background on IETF and the work on header compression and fragmentation at the IETF.
Okay, thank you, Dominic, for this nice introduction. So now I will go in a little bit more details about the IETF. As you say, it's a very huge organization with a lot of working groups. So I'm going to focus only on the transmission, how to create a network, and the IETF design initially, so protocol for computer to exchange information. And it comes to this Slack that you presented, where we have an IP layer, and this IP layer will hide the specificities of layer 2s. So this way you have a very nice stability to develop your application, either because you don't see the specificity of layer 2, and also because this layer is lasting for a long period of time. For IPv4 has been designed 30 years ago. And in fact, this stability is also a problem because the first protocol, IPv4, has a very limited addressing space, and now we are reaching the limit of this addressing space, and a new version is now currently deployed, and it's called IPv6, which are longer address and can address almost anything in the world. So on top of this IP layer, we have to make the link with the application, and we have two protocols that can make this link. One is UDP, that is very, very simple and just contain numbers as port number to designate the application. And TCP do that and has also some complex mechanism to do flow control, error recovery, and reordering packets if they arrive in not the right order. So on top of this, on TCP or UDP, you can build your own application, but the IETF also has developed a protocol that is used for the web. And in fact, we call the web the killer application because the web forces everybody to go to the IP network. And that's why right now we are only using this technology for worldwide communication. So on top of HTTP, we have also, the IETF is also defining some format to structure the information, and it's either XML or JSON. So with this model, as you know, we can do link between application, and we can carry information, communication from machine to machine. And one good example, for example, is the communication between the LNS and the application server in LoRa. But one problem with this stack is that it has been designed for computer, is talking a lot. You have a lot of exchanges. And of course, it fits well for computers. But for constrained device and constrained network, it doesn't work that well. That's why the IETF designed a specific stack or redesigned a specific stack for constrained network and constrained device. And in fact, it used some existing protocol like IPv6. IETF says that don't use IPv4 anymore because there is no more addresses. So when you develop something new, you have to focus on IPv6. But since IPv6 is a little bit big, 40 bytes of header, then they develop also an adaptation layer that is called LoRaWAN, sorry. And on top of that, we have the UDP, because UDP is very simple. You can build your own application, but you can also use a protocol that is called CoAP and is totally compatible with HTTP and is lighter and easier to implement. And on top of this, you have a CBOR representation that is a binary, can be viewed as a binary version of JSON. And this stack works well for constraint network, but not as constraint as we know in LP1. In fact, the target is 802.15.4, as you may find, for example, in ZigBee. So when we wanted to use LP1 network, it was not easy to use this one. So we went to the IETF and we asked for the creation of a working group, which is not an easy task because you have to prove that you cannot do what you want to do with existing protocol, and there is really a need for a new standardization effort. And in fact, when we talk about this adaptation for LP1, the goal was not to develop new protocols because it will be created some interoperability problem. What we proposed, in fact, was to extend the compression mechanism that was initially designed for LP1 to be, so for LoRa 6LoWAN, and to design it for LP1 and to extend it to the full header. And this way, we can have very, very strong compression because we can be in tens of bytes for this compression. So, header compression is not something new. In fact, since the beginning of Internet, we are using header compression. So the first time maybe you have used header compression is when you were connecting with your modem to a phone line to the Internet. So the throughput was very limited by the modem. So the first compression was IPv4 and TCP with a mechanism designed by von Jacobson. So 10 years after, a new protocol mechanism has been designed, and you find it now in your phone when you are in 4G, for example, when you want to do a phone call. So you have a header compression for IP, UDP, and RTP for sending voice over a data network. Then we have 10 years after, we have the 6LoWAN compression mechanism. We talked a little bit earlier, that was dedicated to mesh network like 802.15.4. And right now, we are pushing this new SCHC mechanism that allows us to compress IPv6, UDP, CoAP, so the full stack, but it's more generic than that. So just to analyze these two compression mechanisms, these four compression mechanisms, we can classify them in two classes. So for example, the first one are flow-oriented. It means that at the beginning, you send the full packet, and then you analyze and find some flows. And in these flows, you just send the difference between one packet and the other. So that's good, but for LP1, it doesn't work well because at the beginning, you have to send the full packet, and it's not compatible with some very constrained links. And the other family is packet-oriented networks or compression. And here, it means that you have rules. So in 6LoWAN, these rules are implemented directly in the code. And in SCHC, it's a database that contains the rules. So it's offer more flexibilities and offer you to compress IPv6 UDP CoAP, to adapt this compression to your specificities, but you can extend this mechanism to other protocols. So another part that is important in networks is fragmentation. So what is fragmentation? For example, you want to send a message, but your frame is too short to send the full message. So what you have to do is to send this message, to cut this message and send it in several frames, and you add a small header to give the position of your message. So IETF developed already some fragmentation for IPv4, IPv6, or 6LoWAN, but this fragmentation is not really efficient because when you lose a fragment, the full message is lost, and maybe you have to send again the full message even if only one fragment is missing. CoAP implements also a more efficient fragmentation mechanism, but all the fragment has to be acknowledged, and in LP1 network is not so efficient because you are using the uplink and the downlink regularly. So we need a fragmentation mechanism because sometimes the frames are very small, but we have to do it in a clever way, not to overload too much the network. So now I give the floor back to Dominique that will start to explain the chip technology and the compression mechanism.
Thank you, Laurent. So, what were our assumptions when we started the work at the IETF? The first assumption is that the IoT devices don't download a new application at their will every so often. We assume they very rarely change their application and their configuration, and this only happens when the device manufacturer or application business owner decides to change it. Therefore, it's a rare event and a well-controlled event. We also assume that the critical aspect is the cost of the transmission, of getting the data from the sender to the receiver, be it on the transmit side or on the receive side. And the cost is energy, because those IoT devices are often battery powered, time on air, because on an unlicensed band, we're often limited in duty cycle, and therefore it's a costly resource to use the wireless medium. We assume that the memory is constrained because these devices are need to be low cost, but they still have some amount of memory, and we assume that they are not so constrained in terms of computation. If we compare the energy cost of transmitting 1 bit or receiving 1 bit, it's in the order of microjoules or even up to the millijoule per bit if we're transmitting really slow, compared to 1 nanojoule per instruction on a modern microcontroller. So we can spend quite a lot of computation cycles just to save 1 bit or a few bits over the air. So that's our design principles. We also assume that the link is constrained and we're going to do compression over that link. We're not trying to build a mesh network. So we can simplify quite a lot of stuff compared to pre-existing technology. We wanted to support links that are bidirectional, of course, but also links that are unidirectional. Maybe you don't have a downlink at all in your data plan, or the downlink is costly to you because it's a per packet fee or hard limit on the number of downlinks. Or for a telecom operator, we know that the duty cycle of the base station is a very critical aspect in the system. So we wanted to be able to accommodate that. And also, we wanted to be able to operate over a radio that has variable MTU. The messages can be of variable sizes. And typically with LoRaWAN, we have the adaptive data rate that changes the maximum size of your payload based on the radio conditions and the network decisions. And so we were aware of that and wanted to be able to operate over that. And so what we've done is to provide a compression mechanism that is flexible, that can adapt to each type of device or even to each individual device based on the conditions in which it's operated. We wanted to have a very good header compression, try to remove as much as possible from the unneeded information, as I mentioned before. We wanted to have an efficient fragmentation, even though the message sizes can be very small. We wanted the fragmentation header to be even smaller than that, so that the overhead is very little, and also little control dialogue. We don't want messages going back and forth if they are not needed. So first I'm going to show you a very simplistic illustration. It's not meant to be the description of the header compression that we're doing with SCHC. It's just to give you a flavor of what's going on here. So let's suppose we have a packet coming in that needs to be transmitted over that very constrained, very expensive link. And so you have many bits in that packet. And because the IoT device is always does the same thing, the same application, it's not reprogrammed every day, you can expect a few types of messages, few types of patterns. So you know you're going to be transmitting always the same kind of messages. And so assuming you know those patterns, you will compare that packet that you need to transmit to the expected patterns. And so pattern 1 in this example does not match. So let's have a look at pattern 2. Pattern 2 doesn't match either. Let's look at pattern 3. And in this example, pattern 3 matches. All the preset bits in the pattern match the bits in the incoming packet. And so we know that pattern 3 is a good pattern to represent the message that we have to send. So what do we do? Knowing that the receiver knows the same patterns, we only need to send the number of the pattern, in this case pattern 3. So in this example, that's going to be 2 bits to designate number 3. And then we need to fill in, the wildcards here. Pattern 3 did not completely describe the incoming packet. It left a few bits open. And so we will send those few bits following the number of the pattern. And that's what's going over the radio. And at the receiver, obviously, taking the first few bits here, you can dig pattern 3 out of your database and then filling the blanks with the following bits. So that gives you an idea of how SCHC works. The more complex picture is here. So you have, again, a transmitter to the left of that picture, a receiver to the right, and some packet that needs to be transmitted. So the first thing we do is run a protocol analyzer for the packets that we want to transmit. So we're going to break down the packet into protocol headers and each protocol header into fields. And then we have a list of fields. And then using the context, which is a set of rules that is stored in this database, we're going to compare the list of fields of the protocols of the packet we're going to compress with the fields in the rule. And when we have a match, then we will compress that incoming packet with the actions that are described in the rule. And I'm going to show you that in a little more detail later on. The basic idea is that we want, as much as possible, that the information that is going over the wireless link is just the number of the rule that matched, and maybe a few bits, as few as possible, to fill in the blanks, as I showed you in the illustration before. In the case the compressed packet is still too big to fit the payload of the link, then we have the fragmentation algorithm that kicks in, and we can chop off the packet into little pieces and send them one after the other over the link. So very important, that process is this idea of sending the numbers of the rules that match the packet, and hopefully the number is enough to describe most of the packet. So again, on this picture, we show an incoming packet in purple coming from the left, let's say an IPv6 UDP something packet, and we're going to compress it by finding the appropriate rule, and we're going to send the rule ID that matched with some residue, some compression bits that are needed, and it's going to be reconstructed at the receive end node B using the rule ID and the compression residue. Now we wanted to be able to use this rule because the rule is going to be installed on both ends at the sender node A, at the receiver node B. We figured we wanted to use that same rule also for communication between node B and node A. But if node B has a packet to send that matches the same pattern. So yes, we allow the rules, the compression rules, to be used on both directions with a little tweak that allowed to do minor improvement on the way we process either direction, which I'm going to show you later. We also have a special rule for the rare case where compression didn't work. We didn't find a rule. The packet that came in was too odd compared to the patterns we had in the rule set, and so we need to send it anyway. And so we have one rule ID that's dedicated to sending packets that don't match any of the patterns. And then, if, as I said before, if the compressed packet doesn't fit into one radio packet, then we do fragmentation. And for that, we break the packet in little pieces, and maybe we want to have an acknowledgement because we have, LoRa is going to explain you later, a very smart fragmentation algorithm, and so we need an acknowledgement back to control that fragmentation process. Therefore, this rule ID, the number of the rule, is used in both directions. One direction for the fragments flowing from the sender to the receiver, and another one for the acknowledgements. Therefore, we can't use it in the other direction. And now, if node B wants to send something to node A, it cannot reuse the same rule because it would be confusing to have the same rule ID for ACKs and for fragments. So it's very centered around this idea of rule numbers, rule ideas. And because of that, we decided to make it very flexible, very fitted to the various situations. So often we get asked, how big is the rule ID? Because that's very important. That's first information that you're sending. Is it 1 byte, 2 bytes? Well, it's the IETF standard doesn't say. It depends on your application. And for LoRaWAN, we made a decision. But in general, the IETF standard doesn't mandate that. It doesn't even mandate that the rule ID is a fixed size. It could be even variable size, so you can do entropic coding, assign the short codes for the frequent messages and longer code for the rare ones. So again, shown in a different way, your incoming packet has been compressed, at least the headers that you know about because you have a protocol analyzer for them have been compressed. And you have this rule ID for compression, the residue bits, the bits that you need to fill in the blanks that appear here, and here's a payload, and the payload is whatever you don't have an analyzer for and you're not able to look into. And again, if this doesn't fit the radio link payload, then you will cut it in small pieces, fragment payloads, and prepend them with headers, fragmentation headers. And there might be need for a little bit of padding because all of this is bit oriented. So if you may want, like for LoRaWAN, you want to end up on a full byte, and so you will add a few bits, up to 7 bits, to fill in the last byte. In this slide, we show an example of traffic that's captured, IT traffic that has been captured using standard IP protocols. And the purpose is very much not for you to read the hexadecimal data and understand that, but what we want to show is all those bytes, the 60, 80 bytes that we mentioned before, they don't change that often. Each line is a separate message, by the way. And so you can see here, for example, it's always the same value. Here it takes 2 different values. So actually, in terms of information theory, there's very little information in that. If you can capture that knowledge, put it in a context that's known on both ends, then it's very easy to compress away all this redundant information. And basically, you can compress all these headers into just a few bytes. And so compared to your payload, it doesn't show. It's very minimal. And now I'm going to explain you a little bit further how we do that. And so we have this set of rules that I've already mentioned. Each of these rules has a list of entries. Each entry is dedicated to one field of one protocol of the packet that we are trying to compress. And so it has a field ID, which describes, for example, it's a UDP destination port or IP source address. So one entry for all these, for each of these fields of each of these protocols in the stack. And so UDP and IP are very simple protocols in terms of headers, I mean, and the fields are of fixed size. There's only one instance of each field in the header, but some of the protocols are a bit more complex, like CoAP, for example, which has multiple instances of the same field appearing in the header, and therefore we have a position indicator, which means this entry matches the first occurrence or the second occurrence or the third occurrence. And also CoAP has variable length fields that we need to deal with. And so with this indicator, we say that we're going to have to send the actual length of the incoming packet over the wire, which we don't have to with fixed length fields. And also here we have this direction indicator, and this is a little trick I mentioned before for uplink and downlink. If you look at IP traffic or UDP traffic between two nodes, they're going probably to swap source and destination address and source and destination port, for example. And so with this little indicator, you can reuse the same rule, but just tailor it for the uplink or downlink direction, and so we save memory in our database. So now that I've explained the list of field descriptors that we have, how do we decide that we have a match? Well, for each of the fields, we have a matching operator and a target value. And so far, in the IETF standard, we have found a need for 4 matching operators. Doesn't mean that we couldn't add another one in a new version of the standard, but right now we have 4, and 2 are fairly obvious, the equal one, which means all bits of the field of the incoming packet are equal to the fields, the bits of the target value here in the selector. Or another obvious one is MSB, so we match only the most significant bits of the field. We could also totally ignore that field and match in any case. Or a more interesting one is the match mapping operator, in which case we know the field is going to take a few discrete values, and we're trying to match one of a few values in a target list of values. And so we have the target value, which is a scalar for equal and MSB, and which is a list for match mapping. And so the decision is that if we have a one-to-one correspondence between each field of each protocol of the incoming packet and each field of each rule, so we have one-to-one correspondent, and each of these fields matches with the matching operator of that entry to the target value of that entry, then we have a match for the rule. And then we can decide to use that rule to compress that packet. If we do use that rule to compress that packet, how do we do? Well, we use the compression and decompression action that appears in the rule as well, per entry for each field. So we have a different way of compressing each of the fields of that packet. And right now we have a few compression actions which pretty much correspond to the matching operators. If the field was equal, then the pattern totally defines that field, so there's no need to send anything because the rule identifier will totally allow the receiver to rebuild the field. So we just elide that field, we don't send anything. if we ignored that field, there's no knowledge at the receive end of anything about that field and of the value of that field. So we probably want to send it in extenso over the wire. If we had an MSB matching operator, we probably want to send the LSB. If we had the match mapping, so we matched one among a few in a list, then we probably want to send the index into that list, etc., etc. So that's what we have, and that's the basis to be able to find the amount of information, extract information that's in the incoming packet, and only send a representation of that information, leaving out all the overhead, all the redundant information. So I hope I've convinced you that we've designed a very flexible engine that is compatible with complex protocols at some cost, to be honest. We need to have a protocol analyzer that can understand the complex protocol, and this needs to be running in the IoT device. We also have an engine that's extensible, as I probably told you along the explanation. We could potentially add more operators, matching operators, compression actions if we need to, if we find a need for that in some yet unaddressed protocol. Also, as I've already said, the compression algorithm is bit-oriented, so we're not wasting bytes to get stuff aligned. We're only sending as few bits as possible as is needed to convey the needed information. I already mentioned the entropy coding of the rule IDE, and also we can have a large number of very focused compression rules that will do very aggressive compression. And so we send the minimum number of residue bits, or we could save memory in our database by having more widely encompassing compression rules that address a wider spectrum of incoming packets at the cost of sending more extra bits, filling the blanks, if you will. And so we'll also have this flexibility as we instantiate the header compression mechanism into one device. As we have mentioned before, SCHC means static context, and so this means we can only compress away, we can only elide information that is known a priori. So we don't learn on the fly. The machine is doing the same thing all the time, and it's only doing what it has been instructed to do ahead of time. And so there are things we can't do. We can't guess counters and strides. We don't have regressive models of what's going on in the fields. And that was a conscious design decisions so that we don't have to have a feedback path to adjust that compression algorithm. Another question that is often asked is about encryption. Everybody wants security, of course, and with security we want encryption for confidentiality, and encryption hides away everything that's above. You don't recognize what's being transported. That's the very purpose of encryption, which means the compression mechanism can't see the structure, the headers, the fields, the constant values, and everything that I showed you before. And therefore, if you have a security layers that has encryption, we're no longer able to compress whatever is above that. And so if you really want to do maximum compression, we need to do a two-pass compression, double compression, one compression above the encryption that compresses the upper headers, and another pass at the bottom just before transmission over the constraint link. And this one will do all the remaining headers up to the encryption. So typically you would do IPv6 UDP DTLS outer headers with the lower pass, and do the rest like co-op in the upper layer. That's all I wanted to tell you about the compression, and now I'm handing it over to Laurent for fragmentation. Go ahead, Laurent.
Thank you, Dominic. So yes, I will present you briefly the fragmentation. And as you say, a rule doesn't indicate only a compression, but also point to can point to fragmentation. And in the rule itself, we will put some information regarding the protocol and the format. It means that the standard by itself doesn't impose some timers or some format, and it can be adapted to your needs. For example, if you have very long messages, then you will need very long fields to indicate the position of a fragment in a message. If you have short messages, then your field can be shorter. So we have a lot of flexibility in that, and we also developed three kinds of rules, three kinds of fragmentation. One is called the NOAC mode, and as its name states, it means that we have no acknowledgement. The sender is just sending the fragment, the receiver reassembles them, and we introduce a checksum that is called reassembly check sequence that allows the receiver to see the integrity of the message. If the integrity is not verified, then the receiver will drop the packet. The other mode that requires acknowledgement is called always, and in that mode we cut the message into windows, and we will go from one window to the other, or the sender will go to one window to the other, only when he will receive a positive acknowledgement from the receiver. And if the receiver doesn't receive all the packet from the full window, then he will ask using a bitmap, I want this fragment, I want this fragment. And then sender will have to send back. And then he will when the sender will receive a positive acknowledgement, he will go to the next window. So this mode is quite good, for example, in LoRa for downlink fragmentation, because you have a generation of periodic acknowledgement, and that can be used to trigger the downlink messages. But this mode is not optimal in terms of acknowledgement, and so we develop another mode that is called ack on error, and as its name says, we just send acknowledgement when we detect an error, or when the receiver detects an error. So it's based on the same technique ack always, but if the receiver receives a full window, he will not send an acknowledgement. So this mode is quite useful because you limit the number of feedback. In fact, you can have just a feedback at the end that say everything is correct, and it's a very, very short message. And also, when we do retransmission, the MTU may have changed, and we can adapt to that change. So it's something very flexible and very simple to implement. So just to give an example, so here we have a payload with a compression residue and a rule ID just before, but it missed in this slide. And in the rule, we have a parameter that gives the size of the tiles or that we will use. So what is a tile? It's a way to cut the message into pieces. So each tile has a fixed size that is stored in the rule, and all the tiles have the same size, except the last one that may be shorter. So we have to number these tiles. So we use a double numbering. We have a window, and the window has increasing value, and we have a FCN field, and the FCN field has a decreasing value. And each time we reach 0, then we go to a next window. As you may see, the last tiles have a special number, and that is what we call an all one. So all the bits are set to 1. So in this example, we took the value 7 to tell that it's the last slide. And this way, the receiver knows that the packet has been completely transmitted, and so that he can compute the checksum, the RCS, and see if everything is correct. So what is the advantage of this? is that when we want to send a fragment, we can have any size of fragment, and we will fill this fragment with ties. The only thing we will add at the beginning is a very small header that will contain the window value and the FCN value. And the size of these fields are described in the rule. So if you have very, very long packet, you will need, for example, some high number of bits to number the window. If you have very, very small packet, then you need a smaller number of bits. And of course, you can have both rules, and you can adapt to what you want to transmit. So just see in a small example how it works. So here we are sending a message into fragments. So here we have a window that contains 5 ties, and here our fragment is able to send 7 ties. So it means that the receiver will create a bitmap to say which ties are okay and which ties are, which windows are full and which windows are not full. So here we see that with the first fragment, we fulfill totally the first window. So the receiver will not acknowledge it. And for the second one, we have only 2 fragments that are 2 ties that have been sent. And so the receiver has to, the sender has to send the other one. So we say that the second fragment is lost, and then the receiver receives the third fragment, and here it detects that some ties are missing in the second window. So it will send an acknowledgement saying, I have received these 2 ties, but these 3 ones are missing. So the sender will send back this information, and here will fill all these 2 windows. So everything goes well. At the end, we send a all one message that says this is the end, containing a checksum, and the receiver acknowledges with a short message saying everything is all right. So let's make a more complex example where we are going to change the size of the MTU. So here we have the same scenario, except that now the acknowledgement is not every time, but we can also force the acknowledgement to be only at the end when we have received the last tie. So in that case, we will send a message that say I have received this window, and these 3 ties are missing in this window. And so the receiver will resend what is missing. And so here, since the MTU has changed, so we will need 3 ties to send the same information. And at the end, we have the acknowledgement. So this way, we limit the number of feedback, and we adapt to the size of the MTU. So all this behavior, of course, are described in a rule. So as we say, just to have a wrap-up, so we have something that makes the transmission reliable using acknowledgement and RCS. We have this variable MTU support. The number of acknowledgement is very limited, and we suppose that we have positive acknowledgement when we receive no acknowledgement. And for the implementation point of view, Acon error is very easy to implement because we have a very loosely coupled state machine, and so we don't have to maintain a very high level of synchronization between the 2 sides, so it simplifies the implementation. And we don't need that much memory to store the information. We just need the information and some bitmaps. So it's a very, very efficient mode to do fragmentation on LP1. So now that you have seen the theory, I give the floor to Hussein that will show you how you can apply SCHC in real life using LoRaWAN.
Thank you, Dominique and Laurent, for providing the background and explaining the mechanisms of SCHC. So now I'll be focusing on SCHC as the adaptation layer for IPv6 over LoRaWAN. As you know, the worst case LoRaWAN payload sizes are too small to transport IPv6 headers, and LoRaWAN does not natively provide fragmentation and assembly. So, in line with IoT technology convergence around IPv6, the LoRa Alliance released the technical specification TS010 which specifies SCHC as the IPv6 adaptation layer for LoRaWAN. This technical specification makes use of the IETF standards RFC 8724 and RFC 9011. And as a first important note, the IPv6 adaptation layer SCHC works with all versions of the LoRaWAN, with all regional parameters, and with all classes of devices. Actually, SCHC operates on a point-to-point logical link between two SCHC entities. So within the context of LoRaWAN, these two entities are considered application layer, and they are first SCHC protocol implemented in the application layer of the SCHC device. Second, SCHC protocol implemented as a SCHC gateway northbound of application server or collocated with it. So when a device is using IPv6 applications, headers are compressed, and then compressed messages are fragmented if their size is more than the LoRaWAN MTU, and the resulting information is sent on the LoRaWAN link to the gateway, which forwards the frames to a network server. The network server sends the data to the SCHC gateway for assembly and decompression, and a similar process is done for messages in the other direction with end devices as destinations. Note that the SCHC implementation at the device and at the SCHC gateway should know the context in advance and share the same rules before message exchange. So to identify a SCHC rule, each transmitted message starts with an identifier. As explained, it's called the rule ID. And as per specifications, the port field F port is used to carry the rule ID. And here we have two possibilities. The first possibility, if fragmentation is not applied, and the rule ID used for SCHC compression will appear in the F port of the LoRaWAN frame. And if fragmentation is applied, then the rule ID that appears in the F port field is that of the applied fragmentation, and the compression rule ID is carried in the first fragment payload. Note that the rule ID is 8 bits for SCHC over LoRaWAN and should be in the range between 101 and 223. And for the sake of interoperability, three rule IDs are recommended for LoRaWAN. Rule ID 20 for uplink fragmentation, Rule ID 21 for downlink fragmentation, Rule ID 22 for the case of no compression. So one of the essential points in enabling IPv6 over LoRaWAN is how to calculate the IPv6 interface identifier. TS010 and RFC 9011 specify that the IPv6 IID should be calculated using the EES CMAC algorithm and the device EUI, extended unique identifier, and application session key as parameters. So it's actually the EES CMAC of the key, which is the apps key, and the device EUI. And then the IID is the first 8 bytes of the result of the algorithm, as you see in green in the example in front of you. The AES mechanism that is used is not only compatible with the IETF, but it's the same algorithm defined in the LoRaWAN protocol. So by using this algorithm, the generated IPv6 IID does not disclose the device EUI, and it changes with each change of the device security session. Now, let us have more details of SCHC mechanisms for LoRaWAN. So first point is the compression. So the same compression mechanisms explained by Dominique and Laurent before are used for SCHC over LoRaWAN. So they are the same compression, decompression actions, and this means that we can compress the headers using these mechanisms and then go to fragmentation if required. Second, when padding is required, padding bits are zeros. So this is important and this is required. For fragmentation, we have the case of uplink and the downlink. ACK on error is used for the uplink messages, for uplink fragmentation from the devices to the application, and ACK always is used for downlink from the applications to the devices. Indeed, we have also the case of downlink multicast where no ACK is used. Now let's focus on uplink fragmentation. So ACK and error is used in this case, and this means that the SCHC receiver signals only the missing tiles to optimize the downlink. In addition, 2 bits are used for the Windows index, so this means that up to 4 windows are allowed in SCHC over LoRaWAN uplink. 6 bits are used for the FCN field. Remember that the FCN field is used for sequencing tiles. And this means that each window is composed of 63 tiles. Why 63? Because the FCN field with all 1 bits, so all the bits is 1, is reserved for signaling the last tile of the SCHC message. You'll see this when I present the demo. So, in addition, the tile size should be 10 bytes. So by doing the calculations, we can see that the SCHC MTU is 2,520 bytes, and this means that with SCHC over LoRaWAN, a LoRaWAN link can deliver the 1,280 bytes MTU required by IPv6. Now back to downlink fragmentation. So in downlink fragmentation, ACK always is used, which means that the device will always acknowledge when it receives a SCHC window. One bit is used for labeling the windows. This bit alternates between 0 and 1. We have 1 bit for the FCN field, which is 1 only when the last fragment is sent. Note, a very important note is that there can be no more than 1 fragmented SCHC packet in a transit for each fragmentation rule ID. So this is in the case of LoRaWAN. And it's important to know that we have what we call SCHC timers, and these timers such as retransmission and inactivity timers that are used to trigger retransmission and avoid unnecessary waiting of the receiver for a certain message. So this is to optimize the behavior of the device. Now let us have a look on the format of the different types of fragments used during uplink fragmentation session. So the idea here to see the fragments is to show you that we have different types of fragments, and these fragments are well defined so that it provides its functionalities. So one point to highlight is that SCHC works on the level of bits. So that's why you can see on different fragments that we have a field with 2 bits, field with 6 bits, and so on. And this is actually to optimize the usage of the radio resources. Indeed, we have also the formats of fragments for downlink fragmentation, and to check them, you can refer to RFC 9011 for more details. Now, the million-dollar question, or even more, where can we use SCHC? So with SCHC, many applications can be extended or retrofitted with LoRaWAN connectivity, and this is thanks to compression and fragmentation. By compressing the headers and possibly the payload, the size of messages can be reduced. Also, SCHC fragmentation provides the solution for several applications with message size that actually exceeds the LoRaWAN payload. So this is in general how we can apply SCHC for applications on LoRaWAN. To be more specific, SCHC can enable many upper layers and applications such as DTLS, lightweight M2M, BACnet, Modbus, and others. For the case of co-op, TS10, the technical specification TS10 recommending using RFC 8824, which specify how to use SCHC for compressing co-op. And it's also worth mentioning that ongoing efforts are done to specify how to use SCHC for enabling IPv6 at the IETF, and I'm sure that a lot of you would like to see a ping over LoRaWAN. So I think it's coming soon. One of the usage that I personally expect to highly leverage from SCHC is IPv6 smart home application, which will profit from the LoRaWAN advantages such as long range and low power needs. Indeed, all of these mentioned application and use case need a lot of time to be explained how to be used with SCHC. And I will be focusing on a specific application, which is electricity metering, and more precisely DLMS over LoRaWAN. And an important point here is that DLMS over IPv6 over SCHC over LoRaWAN solution is entirely standardized. So what is DLMS? DLMS is leading standardized data exchange protocol and certification program that guarantees interoperable and secure data exchange to support strategic energy and water infrastructure. So in DLMS, they define an object-oriented data model, an application layer protocol, and media-specific communication profiles. And DLMS actually brings a lot of benefits, such as certified interoperability, scalability, and many others. And in response to the growing market demand, the DLMS UA, the DLMS User Association, specified a new communication profile for LP1, and this is found in the Blue Book Release 14. The meter, as per the specification, the meter sends standardized DLMS conversion data transported in IPv6 packet through the LP1 or through the LoRaWAN network, and to do so, the packets are processed, I mean that they are compressed and fragmented if required by SCHC. So note that the defined architecture, the architecture that you see in front of you, ensure that each layer is implemented according to the standards. This means that the DLMS application environment is maintained end-to-end. The LoRaWAN link is transparent to the head-end systems, and thanks to SCHC, LoRaWAN-connected meters are similar to classic DLMS IP devices, and thus utilities can use LoRaWAN connectivity alone, or they can include it as complement for existing infrastructures. So as I mentioned before, the DLMS specified a communication profile for LP1. This profile is based on the Internet Protocol. Thus, it mandates SCHC as an adaptation layer. So if you want to apply DLMS over LoRaWAN, you have to use SCHC. Moreover, to lower the volume of traffic, to further lower the volume of traffic and optimize the medium usage, the DLMS profile for LP1 recommends first peer association, second push mode. So it recommends push mode instead of session-oriented communication. And this means that the meters are configured to periodically send message, for example, each 30 minutes or 15 minutes, each daily ones, monthly ones. And of course, when required, the head-end system can initiate on-demand query to the meters for specified data reads. This allows maintaining the same level of service and security without with reducing the traffic. Here, it's very important to understand that when I say reducing traffic, I do not mean by any way that the DLMS meters will not send the information required by the utilities. The objective is to optimize the usage of the media resources. So for example, in the front of us, we see a summarized sample profile for DLMS over LoRaWAN meters, where you can see different types of profiles with different periodicity. We have the loaded profile, which can be sent every period of time, as I said, like 15 minutes, 30 minutes. We have the daily and monthly profile that can be used for billing as an example. And indeed, we have specific information that can be requested from the meter. Now I will be tackling a regular question, which is how much SCHC can achieve in terms of compression, with an example on the LMS. So if we consider headers only, this means that we are using SCHC to compress UDP, IPv6, and the LMS headers. So with this, the 48 bytes of the IPv6 and UDP headers and the 8 bytes of the DLMS wrapper can be compressed into 1 to 3 bytes. And this is around 90% of compression of the headers. Now, if we consider the whole IPv6 UDP DLMS message, then SCHC can achieve around 70% of compression ratio. Now, let us enjoy a demo of DLMS over IPv6 over SCHC over LoRaWAN. What is in my hand is a LoRaWAN-based DLMS smart electricity meter manufactured by Kaifa. After measuring many parameters, this meter sends DLMS COSM data over UDP over IP over LoRaWAN by using SCHC. The Akilo SCHC implementation in the LoRaWAN module compresses headers and possibly payloads and apply fragmentation when it's required. There are several types of messages and profiles that are sent by the meter. As an example, the load profile is sent periodically every 30 minutes in this example. It includes many parameters such as energy consumption, power, power factor, voltage, and others. SCHC compresses the message, then applies a fragmentation when the compressed message size is more than the LoRaWAN MTU, where the fragments are sent over the LoRaWAN link to the SCHC gateway. The SCHC gateway reassembles the fragments, then decompresses the packet, and then sends the reconstructed DLMS over UDP over IPv6 to the head-end system. In front of us is the Kaifa head-end system, where we can see the meter readings, request specific parameters, and control the meters. As you can see, the load profile is received every 30 minutes. To check the fragments of the messages sent by a DLMS over LoRaWAN meter, I will use one of Akilo's tools, the SCHC debugger. The SCHC debugger shows the frames received by the SCHC gateway on the left side. In this example, we can see that the message was sent via 3 fragments with rule ID 20. Rule ID 20 is the recommended value for uplink fragmentation. Indeed, the windows and the FCN fields allow the SCHC gateway to follow the tile sequence, and the all one fragment signals that the very last tile of the SCHC packet has been transmitted. Once the SCHC gateway verifies that all the tiles are received, it replies with an acknowledgement. The SCHC gateway reassembles the SCHC message and then decompresses it as shown on the right side. We can also check the decompressed message where the IP and UDP headers can be easily recognized. In addition to checking the event logs, controlling the meter, and reading parameters of different profiles, the head-end system can request specific parameters from the meter. For example, let us request the voltage. As you see, the SCHC packets appear at the SCHC gateway, and we see the voltage in front of us. Finally, it is important to know that you should follow the Blue Book from the LMS UA, TS010 from the LoRa Alliance, RFC 8724 and RFC 9011 from IETF in order to achieve a compliant DLMS over LoRaWAN electric metering solution. So I hope that you liked the demo, and in order for you to integrate SCHC technology within your products, Akilo opened the developer program to the public. And this is actually the place where you can find anything you need for IPv6 based LoRaWAN solution. The community edition solution allows you to have free access to the technology with rich and well-documented open source examples, including the DLMS. By registering, you will have access to SCHC library, to SCHC gateway, to the IP core, to open source examples, and to detailed online documentation. Furthermore, the device firmware developed within this program is free to be used including in commercial products. So with this program, you will have IPv6-based solution over LoRaWAN for a radically short time to market. And based on our experience, this is around 1 week to 1 month. So you just have to register using the provided link. So try it.
Thank you, Hussein. So we are reaching the end of this technical webinar, a marathon for the speakers, but I hope a great tons of learnings and good things for the developers, engineers who attended. Let me summarize as conclusion the 6 key takeaways. Firstly, you have an official release by the LoRa Alliance of this technical specification document about the IPv6 adaptation layer using SCHC. You have into this document all the references to the RFC of IETF and also how to configure, rightly use SCHC for LoRaWAN. That's important because the association creates standards that are the fundamentals to allow certification. And in the LoRa Alliance, we have a task force for IPv6, and we have also a task force for the certification. This second task force I'm chairing also is preparing for very soon, very end of summer, the availability of a SCHC certification process. It's important to remember that the IETF creating a standard for internet, all the famous internet protocols, as Laurent explained, come from IETF, and step by step, they have improved the efficiency and created the support for LP1, which was an important tipping point in the IETF evolution. But the IETF does not certify. The IETF is not a body that creates certification for devices. This is why the LoRa Alliance is reusing this IETF RFC and creates all the fundamentals to allow certification. One of the good reasons for having a certification is, of course, the interoperability between end devices. The utilities, typically, they want to have electricity meters, water meters that can speak DNMS and that can be interoperable. So this is one of the drivers for this standardization and certification effort. The choice by the DNMS Association and the LoRa Alliance together to go with this IPv6 adaptation layer. We have understood in this webinar there are other applications that are leveraging SCHC. The Internet Control Message Protocol, for example, which is under work in the IETF working group for LP1, but also other DTLS, lightweight M2M, BACnet, etc., that will benefit. We are thinking of enabling new markets. Electricity metering is the first one, but others are to come. Definitely, the creation of a developer program by Clio is making much more easy the access to SCHC technology. And as you've seen, they have proven very good performance level, 90% of header compression, 75% of a typical DNMS data, without losing or reducing the key information data that utility needs. So that's essential to see this technology is flexible enough to support different protocols, can be reused for supporting other applications that are based on internet. So definitely we are converging towards an internet world, as Dominique, Laurent, and Hussein explained. All users are making success with the web. So the choice of web technologies is important also for the LoRa Alliance success. We invite you to come to Paris for LoRaWAN World Expo event, where you will be enjoying to see a demo during this event. And again, others activities will explain, present, and speak up for the adoption of LoRaWAN in many verticals. Now let's go for the question and answers session. You can use the question box that is available on the console of your screen. If you want to share some feedback, please use this email address. And again, if you want to scan with your smartphone directly now, you can access to the website for registering to the LoRaWAN World Expo in Paris next July 6 and 7. And now it's time for the question and answers session. So we have already several questions to be addressed to the panelists. So for the first one, to Hussein, this question, very simple. You were speaking about energy meters in the demo. Do you know if these energy meters are already available for LoRaWAN in Australia 915? And also, are they also available for LATAM market? Perhaps you can transfer the question.
So actually, yes, such meters are available. We are actually trying a pilot there. So for who's interested, they can send me an email to give them more information about this. So I'll type my email in the answer and send it. I already did. I typed my email, so please reach me on my email in order to give you further information.
And to continue with the availability of the SCHC library, there is a question: will the SCHC library available for maker hardware like Arduino or SCHC like LoRaWAN boards? And also the second question, are the SCHC gateway open source or available on SaaS only?
Okay, so as Akilio, as I presented, we opened the developer program where you can see SCHC implementation in order to be accessible by many and to prototype and make the implementation. We provide the SCHC gateway as a SaaS. So currently you can go there, you can download the library that you can use for different types of demos, and you can use our SCHC gateway or what we call IP core in order to try it. So there are several, let's say, hardware that is supported. They are mentioned in the demo, they are mentioned in the developer program, and please check them.
Okay, thank you. I will come back to you later. I have a question for you, Dominique. In your presentation, you mentioned that encryption at application level is not recommended since it prevents efficient use of SCHC. Do you confirm that encryption at lower layers is still possible and still efficient?
Thank you for the question, Benoit. I don't think I said encryption is not recommended at the application level, but just that if you want to achieve maximum compression, you will need double compression. But usually customers, especially on a model of a public network run by an operator and then somebody else running an application on top, you probably want to have that kind of encryption between the network layers and the application layers. And the second part of your question is Encryption at lower layers still work. Yes, they still work. They're still efficient. That's part of the LoRaWAN. We're actually operating on top of LoRaWAN. It's seen as an application server, if you will, by LoRaWAN. So it's really over the top of the LoRaWAN network. So the encryption at lower layers, security at lower layers still work, of course.
Okay. Thank you for the answer. And another question to you also, Dominique, for LoRaWAN communication, how the SCHC adaptation layer manages duty cycle and fragmentation?
So I'm not sure about the question. Maybe I'll give it a shot, and if I don't answer, please rephrase the question. But what I can say, as I just said before, we're on top of the LoRaWAN stack, so the duty cycle is entirely managed by the LoRaWAN stack, and so we don't interfere with the duty cycle at all. And then fragmentation, yeah, we do send multiple fragments, but the underlying stack will meet the duty cycle limitations anyway. So
yeah, so SCHC already has a fragmentation system, so it's included, but the duty cycle is managed by the network.
Yes.
If not enough clear, Amaury, you're free to re-ask the question. To continue, also, I had my question to you. What are the benefits of SCHC for a LoRaWAN operator?
Well, we have a benefit for the customers because if you send smaller packets over the air, you spend less energy. So our customers see an increased lifetime of their device running on batteries. So that's one. They're happier with the new system than without it. And also for us as an operator, especially on the downlink from the gateway to the devices, there's a significant constraint. The duty cycle is a significant constraint on the gateway, radio gateway, and therefore, if the packets are smaller, we can serve more devices. So clearly a benefit to both the customer and the operator.
Okay, thank you. There is also this question for you, Laurent. You explained well the history and how the internet was born for connecting computers, but then when arrived the IoT and the need of creation of 6LoWPAN arise, and so the IETF struggled to make it happen 10 years ago. Now SCHC has been released for the LPWAN networks. Could you tell us more about the future, how it looks like? What would be the next steps with the IETF?
Okay, yeah, so the next step, so the standardization process is still on, and we improve more and more SCHC. So the next two improvements, the first one I think is about management of devices. So the goal is to have a better integration of devices into the internet, and one goes through ICMP handling. So we are working right now to compress also ICMP, so it can be benefits in two ways. For example, if your device is sending to a server and the server is not accessible, so ICMP can tell it to the device, and the device can reduce its sending rate, and this way they spend less energy. And the other thing is to use pings. So from the internet, you can ping a device, but the ping will not reach your device. It will just be stopped at the SCHC core, and the SCHC core will answer. So it's a way to manage your device easily without not overloading the LPWAN network. So this is one thing we are working on. And the second thing is to standardize the rule representation using something that looks very, very, very complex, that is the Young data model. but in fact, it leads to something that is very compact, very manageable, very flexible, and it will help a lot the interoperability between different SCHC implementations.
Great. To continue also with a question we have from the audience, LP1 node with IP address can be accessed from a third-party web-based application, provided an IP address of the node is known. Can you elaborate more with that?
Yeah, I don't understand well the question, so you can add some comments if I don't answer well. But yes, if you put a third-party web address into the rule, then you can reach this application, this server.
I think the question was the opposite, Laura. Can the device be reachable from the internet?
Okay, and
of course,
yeah, yes, it can, if you accept it. Yes.
Yeah, you don't need to have to. If you desire to, it could.
Yes, but that's one interesting thing, that if your device has an IP address, so it's easier to integrate with other devices that have an IP address.
Yeah, and that's, I would say, a good way for silo technologies to remove barriers and to allow interactions between different IP-based devices.
Okay.
Perhaps a question again for you, Laurent. The question from Mahfouza Khatoun, is the SCHC layer deployed only on the gateway, or it can be deployed in the sensor as well? I think it's about the architecture and what we call the SCHC gateway.
Yes, in fact, you need two SCHC instance, one in a device and one in a gateway, because you have compression on both, compression and decompression on both sides.
Yeah, and there was a good slide of architecture in the part of SCHC application with Aclio. Then I will continue with a question to you, Hussein. What are the first implementations of SCHC today?
So actually, the first application that is totally standardized now, and we're testing it in the field, is the DLMS over LoRaWAN. So this is the first application. Of course, we can think about several ones, like I said, in terms of IPv6 based home application. But currently, the main application is DLMS over LoRaWAN, and because it's standardized, because it requires IPv6, we can think about IPv6 as unifying, which means that if there is, let's say, several technologies, so you want to use LoRaWAN with another technology, with another LP1 or another communication technology, and IPv6 is the best way in order to unify.
And do you have any results to share from this first implementation and field test?
Mm-hmm. So we have been testing a pilot of meters over several months, and we achieved a very high success rate, so almost 99% of data collected. Okay,
so that's confirming it's a very I would say beneficial to energy meters, but can you also say about the use of DLMS, if there are other use cases with SCHC to support DLMS?
I did not get the question. Other than DLMS, you say?
Energy meters.
So if I understand your question, you want the examples of application other than DLMS, right?
Other than electricity metering with DLMS.
Yeah. So whenever you, for example, whenever you have an application that is limited by the LoRaWAN MTU, so it needs like to fragment the message over several fragments, SCHC is the solution. Whenever you want to go into compressing certain headers. I have mentioned several ones like Modbus and BACnet, where we can use SCHC as, for example, to allow these applications over LoRaWAN.
Okay, so that's related also to another question. Can we support IPv4 as it's used, for example, for BACnet?
Yes, yes, yes.
Okay. Laurent, again, if you want to comment on that, or also to comment on how 6LoWPAN, for example, could benefit also eventually from SCHC.
Yes, just to answer to IPv4, we have a very flexible compression mechanism, so it can apply also to other protocol, and IPv4 is one of them. On BACnet too, it's not that difficult to compress. It follows the same behavior. The other question was about the 6LoWPAN. Yes, so in fact, when we start the standardization at the IETF, we say we are going to focus on the star topology, and we have mesh topologies that are handled by 6LoWPAN. And now we realize that we can have some bridges between these two technologies. This means that 6LoWPAN can remain for the mesh network, but there is no upper layer compression in 6LoWPAN, and so we can have a merge about SCHC technologies and 6LoWPAN technology. We are working on that at the IETF because in fact, we have uplink and downlink, for example, which is very, very LP1 oriented. And when you have a mesh network, there is not this notion of uplink and downlink. So we have to rearrange a little bit the standard, but it works quite well.
Okay, very great. And I have a last question, and then we will close this. Hussein, for example, if you don't mind, could you reply to the question, how does SCHC handle changing destination IPv6 addresses?
Okay, so SCHC was designed to address static context. So you should know how things change or how things are static. If you know that your address or the address of the application server is changing, you will choose a certain compression, decompression action that match the behavior. So if you know that it is one out of, let's say, 5 or 6 possibility, then you can use match mapping. If you know that, for example, only a certain part, only the least significant bit, so you use MSD, LSD. And if you do not know anything about it, then you send it as it is. So the flexibility of SCHC allows to take into consideration many possibilities. Okay, we will lose some, let's say, some compression ratio, but it will still be working.
Okay, so that will conclude this Q&A session. Again, I want to thank you all the panelists, Dominique, Hussein, and Laurent, for your great support to this webinar. You have also access to different material they have proposed in the console. The slides will be made available by the LoRa Alliance again. And if you have any further question, you can contact us directly, as mentioned in the email address of the LoRa Alliance. We invite you also to make a visit to the LoRaWAN World Expo, where there will